Good morning. So, in case you didn't see, homework 3 has already been posted. John will post some mini assignments for next week shortly. And so today, in my final lecture before I hand things over to Gong, we're going to think more carefully about what happens if we try to do perturbation theory beyond tree level. So by tree level, I mean a diagram that has no loops. So for instance, a diagram like this looks like a tree because there are no topological loops, versus a diagram like this contains loops. So this is a tree diagram. This is a loop diagram. And if you recall, on Monday, when we were discussing the LSE formula, I claimed that it was inconsistent with our derivation of the LSE formula to simply take our Klein-Gordon Lagrangian and add an interaction term. This is exactly what we did yesterday. We just assumed we could add an interaction term. That's okay in general at tree level, but once we go beyond tree level, that's not necessarily a consistent thing to do with the way we derive the LSE formula, because our derivation of the LSE required that the vacuum expectation value of the field operator was 0, and that the form factor, k phi omega, was e to the I k dot x. And we said that if we took some naive Lagrangian, we could impose these conditions as long as we were willing to shift and rescale the field. And so today we're going to do that and see what these conditions tell us about how to do perturbation theory beyond tree level. So this is an introduction to the subject of renormalization that will, so it's a big subject and we can't do all of it in one lecture. We'll come back to this in a lot of detail in 52. Also in your statistical physics course, you'll look at some of the same ideas from a different perspective. Okay. So these two things are inconsistent. So after we shift and rescale, what we get, so shift, rescale, and rename, what we get is some Lagrangian that we can break up into a free and an interacting part. And, well, so the shifting and rescaling, so we still want our free part to be the Klein-Gordon part, because that's a theory we've solved. We know what all the states and operators look like. So we'd still like to do perturbation theory around the Klein-Gordon, free Klein-Gordon theory. But shifting and rescaling will introduce additional terms. So we might get a different coefficient in front of our phi cubed term. And so say there's some extra coefficient zg times g, which is what we wanted to put there. And in general, we'll get some other things, which I'll call counter terms, because rescaling will, in general, change the coefficient of the kinetic term and the mass term, and shifting will generally give us a linear term, which we didn't want. So I'm breaking up the Lagrangian into the free part we know how to solve, the part we want to add, and everything else I'm calling a counter term. The stuff we're forced to add are the counter terms. And so what are we forced to add? We're forced to add something. We're forced to rescale this, so we should have a coefficient z phi in front of that term. and we're just subtracting out the free part. So what we're left with is this, and the same for the mass term. And then we are also forced to add a linear term. And so the goal of today's lecture is to try to understand what these conditions tell us about these coefficients. And so, well, let's do some parameter counting first. So we started off with a theory with two parameters. So what we were trying to describe was a massive scalar field. So one parameter we need to describe that theory is the mass. Another is the interaction strength. We wanted to add some cubic self-interactions. So we expect there are two physical parameters in our theory. And so our new theory should also contain two physical parameters. And so we have here, we just look at our parameters. Over here we've got four. We've got zg, z phi, zm, and y. So you can fix two of those parameters by demanding that in some way that we'll discuss later that it matches up with the physical theory we want. And the other two conditions are going to come from these conditions we imposed when we derived the LSE formula. So we've already got two of our conditions from the LSE, and we'll need two more that will in some way specify which physical theory we're looking at. So that's what we'll that's what we'll discuss. We'll try to see what these conditions imply and what the other two conditions should be. And so what we're going to do is we're going to determine the zi's and y perturbatively. And what we expect is that the zi's are all 1, possibly plus some corrections, and the y is 0 plus some corrections in G. So we're going to determine these perturbatively in our coupling G. We expect this because, well, if we turn off our perturbation, we expect we go back to the free Klein-Gordon theory where there's no issues with these conditions. And what we'll find, in fact, is that the order G contribution to Zi vanishes. So this is actually a G squared. Here's a linear contribution to this one. Okay. So that's where we're going. We're going to try to do this, and we'll get most of the way there. We'll get some expressions for some of these quantities. And so let's start with, so we already know two of our conditions. We need two more. We'll come to those later, but let's start with this first condition, because this is the simplest condition. So our first condition, first renormalization condition, is that the vacuum expectation value of the field operator should vanish, or in other words, the one-point function should vanish. And this is something we learned how to compute yesterday using Feynman diagrams. So let's do that and see what the Feynman diagrams can tell us about how this condition works, how we can impose that. Okay, so if we want to compute this using Feynman diagrams, our result from yesterday was that we should draw all Feynman diagrams with one external point and any number of vertices with no vacuum subdiagrams. Okay. But before we compute that, we need to determine what the allowed vertices in our theory are. So the theory we wanted to deal with just had a single vertex. We just had a single interaction term. Shifting and rescaling meant we got not just a cubic term, we also got some quadratic interaction terms and a linear interaction term. So our vertices in this theory look like this. So in position space, the Feynman rule for this one is IZG, G, integral d4x. We also have a linear term, which I'll draw like this. So this is a vertex with only one leg coming out of it. It looks a bit strange, but I'll denote the fact that it's a vertex, meaning an internal point, and not an external point by putting an x on the end of it. And so the Feynman rule for this is Iy integral d4x. And we also have two quadratic terms. One of them involves derivatives. So the expression is going to be much simpler to write in momentum space. So I'll defer that to later when we look at things in momentum space. But schematically, it's going to be something like this. And we won't actually need an explicit expression for this at this time, so I won't write it yet. But this, again, is a not just a line, but it's a vertex with two lines coming out of it. Okay.
Why isn't it just like I m squared times em minus 1 times an integral?
That would be the interaction for this term. But we also have here a term with two fields and two derivatives. So in momentum space, this will be involve k squared. We could separate these out and say that, yeah, exactly what you said would be the Feynman rule for this one. We'd also have a second quadratic vertex, and so they have the same type of fields going in, so it's more convenient just to lump them together, draw them with a single vertex. Okay, so let's draw the Feynman diagrams to contribute. And so we've got one external point, so I'll draw the external point with a dot. And so we want to draw all possible diagrams that have one external point. So one way we can do that is we can use this vertex, just attach a single vertex here. The line ends. So that's one diagram. Another thing we could do is use the cubic vertex, draw a diagram like this. With a single vertex, that's all we can do. We could draw diagrams that have more vertices, so something like this. It's 3 vertices. Or something like this also has 3 vertices. And there'll be lots of terms that involve more than one vertex, but just to see how things work, we're going to focus on these diagrams. So for now, because these diagrams are the only diagrams that have order G contributions. So when we're imposing these conditions, generally we can't do it. It's not always true that we can impose these conditions exactly. But what we'll try to do is determine what these coefficients have to be interpretable. These are the leading diagrams, so we'll focus on these. OK, so let's use our Feynman rules to write down expressions for these diagrams. To do that, it'd be useful to label them. So we have here an external point x, an internal point I'll call y. And the first diagram, we have one vertex, so we get a factor of iy integral d4y. And we've got a single propagator from x to y. And so that's our expression for the first diagram. Our second diagram has one cubic vertex. So it's I, zg, g, integral d4y. And then we have two propagators, a propagator from x to y and a propagator from y to y. And any other contributions will involve at least 3 vertices, so there'll be at least order g cubed. And if we're looking for the leading order contribution, we can set zg equal to 1, because the higher order term will contribute at higher order. We've already got a factor of g here. Okay, so let's simplify what we've got. So we can factorize things. So notice that this Feynman propagator here is delta yy is delta f of y minus y, because the Feynman propagator is translation invariant. So this is actually independent of y. So we can pull this out of the integral. So what we get is iy plus I zg g times delta f of 0 times this integral. We said zg to 1, so just ig. And I forgot something. So this diagram, of course, has a symmetry factor of 2. So there should be a half here. Yes?
Shouldn't there be a sign difference because of the different signs in the vertices? One is minus iy, and the other is icg.
Yes, there should be. The way I've written it here. So I have not been consistent with signs. So both the terms in the Lagrangian I've defined with a plus sign. So they should have the same sign here. So it should be both plus. So the sign in front of an odd term in the Lagrangian is convention dependent. It's a good idea to put a minus sign in front of an even term. Okay. So this gives us an expression for y at leading order. So we should have that y is minus a half g delta f of 0, because this thing doesn't vanish for general x. So the only way that this can be 0 is if this coefficient is 0. So there's only one small issue with this, which is that if we write this out, we get the Feynman propagator at 0 is the integral d4p for 2 pi to the 4th I over p squared minus m squared e to the minus I p times 0, which, so this is 1. And for large p, that we've got four p's in the numerator, two p's in the denominator. So for large p, we'd expect this to go like p squared. So this diverges. Okay, so we can set this to 0 as long.
Sorry. Should this be O of g cubed on the left-hand side? And when you write out the diagrams, have you written out the first order?
First order? These diagrams here, these are O of g cubed. So they all, this one has 3 vertices, which are, have a ZGG, so that the contributions there start at g cubed, and same here. Assuming that y,
Yeah, okay.
assuming that y starts at order g. So we can impose this condition at the cost of having an infinite counter term, an infinite term in our Lagrangian. So that may concern you, but it's, in a sense, not that different from what we saw in the Casimir effect. So there, we ran across intermediate quantities that were not directly observable. In that case, it was the vacuum energy, which diverged, which is not as serious a problem as it seems, as long as the divergences cancel out of anything physical that we can measure. So it'll be the same case here. So this is a divergent term in our Lagrangian, but we're not directly measuring the Lagrangian. We're measuring cross-sections or decay rates or properties of matrix elements or correlation functions or vacuum expectation values. So that's what we can measure. So as long as this divergence cancels out of anything we can observe, we shouldn't be so concerned. Well, maybe we can be a little concerned, but it's ultimately not a insurmountable problem. And the way we typically deal with this is very much analogous to what we did when we were studying the Casimir effect. So we can introduce a regulator. So that's some prescription for making, in this case, the integral finite. In the previous case, it was making the sum finite. So we change all of our integrals so that this integral is convergent, do our calculations, and in the end, we remove our regulator. So there's a number of ways we can do this. One is just by introducing a UV cutoff. This is basically what we did when we were studying the Casimir effect. The first way we did it in lecture was we just cut off the modes beyond a certain point. We could do that here, say that instead of this integral going up to arbitrarily large momentum, we just cut it off at some momentum. And then we could do our calculations, and at the end, send lambda to infinity. And if we had done our calculations correctly, our results should be independent of lambda. We could do it in a number of other ways. So another way that we've examined is dimensional regularization. We saw that in math for QFT. And so that's changing the dimension of space-time to be, instead of 4, to be 4 minus epsilon. So if epsilon is big enough, this integral could converge. There's fewer factors of p in the numerator. So the convergence improves as epsilon gets bigger. And again, we could impose this regulator, do our calculations, remove it at the end. It should be independent. And a third way we could do this is Pauli-Villars, which basically we multiply the integrand by lambda squared over p squared minus lambda squared plus I epsilon squared and we can think of this as coming from a fictional heavy particle that would give us extra diagrams that could remove the divergence. And so as we'll go through, we'll mostly focus on this one in QFT, but we'll make some references to the other methods later. But the procedure is very much the same as what we did in the Casimir effect. So the procedure is we introduce a regulator, then we compute the observable, and then we remove the regulator, which, if we've done our calculations correctly, should not appear in our final expression for the observable. So that's what we could do here to deal with the issue that this counter term is divergent. Okay. But and so for many of these other counter terms, we'll have to go through this procedure. For this particular counter term, there is a nice graphical way to see the effect of it. So just want to see that. Let's look at some other diagrams to see what the effect of this counter term is. So basically, what we just did at leading order is we set the 1-point function to 0, which in terms of Feynman diagrams, that means we're summing all diagrams that look like this. So the sum of all diagrams that look like this should be 0. So this shaded region here just indicates any subdiagram with no external points. And diagrams of this form are called tadpoles. So a renormalization condition is to set the sum of all diagrams of this form to be 0. OK, so let's suppose we've done that. And we can do that by the procedure I've just outlined there. Let's suppose we've done that. And then let's suppose we're interested in computing the 2-point function. So the 2-point function will contain diagrams like this. At second order. But if we've imposed this condition, that tells us that the sum of these two diagrams will be 0. Because basically, what was going on at y up there didn't talk to the rest of the diagram. Basically, whatever we just factorized out, whatever was happening at y. And the same thing will happen here. So this part of the diagram down here won't have any influence of here, and we'll get the same sort of factorization. And so these diagrams will vanish if we add them together after we've imposed this condition. And so that's more general. So if we sum all diagrams of this form, we should get 0 if we've imposed this. And this generalizes too to any endpoint functions. So the sum of all diagrams with tadpole subdiagrams cancel. So there's no need to compute them. So as long as we're imposing this renormalization condition, we don't need to compute any diagram where some part of the diagram is only connected to the rest of the diagram by a single point, single internal point. So this is a huge simplification, and you can see that there's, in addition to the vacuum diagrams, there's another huge class of diagrams that, in general, there's no need to ever compute, as long as we're imposing this renormalization condition. So that's a big simplification. Okay. So that's our first condition. Our first condition basically told us just throw away any diagram with a tadpole subdiagram. Let's see what our second condition is going to tell us. And so this condition, as it's written, is in a particularly inconvenient form. It's partially in position space, partially in momentum space. We wrote down Feynman rules for calculating in position space or momentum space. We could construct some hybrid rules, but it doesn't occur frequently enough to be worth our effort. So let's just look in first position space at the 2-point function. So this is, remember, this is a one-particle state, and we wanted to, in our derivation of the LSE formula, we wanted to interpret phi of x acting on the vacuum as a one-particle state. So this is like a propagator, half Fourier transformed. So we'll just undo that Fourier transform and first look at the position space 2-point function and see what that condition tells us about the 2-point function. So we want to look at is this or this with time ordering. I'll leave out the time ordering for now. After all, they're closely related. We can just add together 2 copies of this to get the time-ordered version, multiplied by Heaviside functions. Okay, so there's actually 2 nice results we can say about this propagator in an interacting theory. So, yes.
Do we assume that the sum of all diagrams with tadpole subdiagrams cancel separately in each order of the perturbation theory, in the perturbation expansion, or just all of them together?
They should cancel at each order. So
Each order separately.
each order separately, yes. So at leading order, it's just the calculation we did. We could go to higher orders. And so if we have this expression is equal to 0, it should be equal to 0 at every order in G. So that we can't write down a series expansion that vanishes for every value of g unless it vanishes at every order. Okay, so there are two very nice and important results or statements we can make about the propagator and interacting theory. So we've computed it. We can compute this exactly in the free theory. So that's something you've all done. We've discussed repeatedly. So let's see what statements we can make about this quantity in the interacting theory. So the first result I'm going to sketch a derivation of is known as the Chalian-Lemon spectral representation. And the basic idea about where this comes from is that we can insert the identity, a resolution of the identity in here. And, well, it's an interacting theory, but we still should be able to write the identity as a sum over the 0, 1, and multi-particle states. So if we have some state, it's either a 0-particle state, so we can project onto the 0-particle states by acting with this operator, or it's a 1-particle state. Or it's a multi-particle state, or some superposition. So we'll write multi-particle states like we did on Monday. We'll specify the total momentum by k and all the other parameters by sigma. So this is the 0 particle. This is 1 particle. This is multi-particle. I don't know if you can read this. This here says K sigma, K sigma. Okay. And so the nice thing about inserting the identity in this form is that this involves the physical energy and momentum of the states, and the physical energy of the states shows up here. So this we've written the identity in a physical way that involves the energy, which will involve the physical mass of the particles. And so this integral, our Lorentz invariant integral, Lorentz invariant measure, can be written, as we saw earlier, as a 4-dimensional integral times a delta. And here, the energy squared is k squared plus the physical mass squared. So this mass here is the physical mass of either the 1-particle state or the invariant mass of the n-particle state, or in other words, the center mass energy of that n particle state. Okay. So that suggests if we insert this identity, well, what are we going to get? So this first term here is going to give us 0 because of our assumption before that the vacuum expectation value of our field operator is 0. So this first term just gives us omega phi omega, omega phi omega, which each term in the product is 0. So this term gives us 0 by our assumption. This term is going to give us something that looks very much like what we had in the free theory, except it will involve the physical mass. So if we write out this term, the first term is going to one particle term. Will look like got the integral and then we've got omega phi of x k phi of y omega, and by the same assumptions as in the LSE formula, this is just the form factor. So this is e to the I ky and e to the, getting the signs right, e to the minus I k dot x. So, and we can, well, maybe the other form is more familiar, but that's basically just one of the terms we had when we were deriving the propagator for the free theory. The difference is that the mass here that shows up is the mass, the physical mass. So what we'll get is if we Fourier transform things, we'll get that 2. So this is the Fourier transform of our 2-point function. This should be equal to the one particle term is just if we combine it with the two different time ordered piece. Sorry, there should be a time ordering here. Yeah. Or a transform of the time ordered product. Combine the two time ordered terms like this, just like what we had in the free theory, because this is e to the I k dot y, this is e to the minus I k dot x. We get a term that just looks very familiar. Exactly the same thing we had before. And we'll also get a contribution from the multiparticle term, which should look pretty similar. The difference is that we'll have, instead of these nice form factors, we'll have some extra stuff. We can't assume that the multi-particle form factor is just a nice e to the iky. There might be some extra contribution. So we'll get some extra term that looks like this. Where this rho of S is what's known as the spectral function. And it describes what the allowed center of mass energies are in the theory. So we could have a center of mass energy equal, if we have a one particle state, equal to the physical mass squared. Or we could have, assuming there's no bound states, we have two particles at rest relative to each other. We could have any sort of center of mass energy greater than or equal to 4 m physical squared. And this basically just comes from the fact that if we write the measure like that, those EKs in the multi-particle integral just involve delta functions that involve the invariant mass of the multi-particle states, or the center of mass energies of those multi-particle states, which start at, assuming there's no bound states, 2 m physical squared. So there's some algebra in between what I've done and what's our final result, but it's exactly analogous to what we did when we computed the Feynman propagator in free theory. So this is an exact result.
Sorry.
Yes.
So revise this integral should be 4 m squared.
M physical squared. Thank you. So this is exact. This is the Chalin-Lemon form of the propagator. Okay. So what are the key points to take away from this formula? So this tells us, in particular, that the now in momentum space, the two-point function, the propagator of the exact theory, has a pole at k squared equals m squared. We can make the same statement in the free theory. In that case, there's no distinction between the mass that shows up in the Lagrangian and the physical mass. But here, we've made a statement about the exact propagator that relates it to the physical mass. So if we can compute things in perturbation theory, we better have a propagator that has a pole in the correct location. The location of the pole in the propagator is a physical thing. That is the physical mass of the theory. And also, furthermore, we get the residue is fixed also by this argument. So the difference between the free propagator and the interacting propagator is basically just all this multi-particle stuff. Because if we act with, or there's a couple of ways to think about it. So if we act with a field operator in the interacting theory on the vacuum, well, maybe we can say that creates a one-particle state in the far past and far future, but at intermediate times, it'll also add in some multi-particle stuff. Or a related way of saying it is that the creation and annihilation operators, the creation operators that create momentum eigenstates in the interacting theory mix as time evolves. So we wouldn't expect that we just get something that involves the one particle states like we did in the free theory. We also got some multi-particle contribution. Okay. Any other questions on that? Katie.
So, in practice, which propagator do we use? Like, if we're trying to use the Feynman rules, do we use that one or the one with the Lagrangian mass?
Okay, so if we're calculating things using the Feynman rules, our Feynman rules relate everything back to the Feynman propagator, which is defined to be the propagator in the free theory. So that would be, the Fourier transform of that would be just this term, or with the mass in the Lagrangian. So what we're going to do after break is we're going to compute this thing using the Feynman rules, which involve the free propagator, which in Fourier space is just this term with a Lagrangian mass. And we should get the same thing. So we know what we have to get exactly. This part is hard to compute in practice, but we know this part has a very physical interpretation and simple. So we should at least recover this part when we compute it using the free Feynman propagator. Alicia.
Oh yeah, so this result does not depend on the strength of the coupling.
No. So I didn't make any reference to the Lagrangian or perturbation theory and derivation on a rough sketch of the derivation. I didn't fill in all the details. Okay, so we've sketched out a derivation of an exact result for the propagator of an interacting theory. And so we want to see, what we're going to do next is we're going to see what this tells us about our counterterms. So what renormalization conditions making the perturbative calculation we can do for this exact for this quantity with our exact result. So those perturbative calculations should match our exact result. And so let's compute that. So G2, okay. So what is this? This is not quite the same thing that we've written down any Feynman rules for. So what G2 of k is the Fourier transform of the position space time order product of two fields. So, well, we can guess what our Feynman rules are going to look like and which Feynman diagrams are going to contribute. So when we did the LSE formula, basically we took our expectation values of time order products of fields, we Fourier transformed, and also applied the Klein-Gordon operators. So we, and that the claim was there that was equivalent to amputating the diagrams. So we're just Fourier transforming. We no longer need to remove the corrections to the external legs. So that'll be the difference between what we're doing now and what we did before. So this is just the Fourier transform of our position space diagrams. So we can draw exactly the same diagrams and just write our Feynman rules will be in position, no longer in position space, they'll be in momentum space. So the diagrams that contribute So it'll be the simplest diagram, just the single Feynman propagator. We also can have corrections, various types. So have diagram like this, diagram like this. Other diagrams we contribute with at order g squared to be something like this. But we've already seen in the earlier part of lecture that these diagrams don't contribute. So at order g squared, these will be the only diagrams. You can go to higher order. Get diagrams like this. And there's lots of diagrams at higher order. And the reason I've drawn out so many diagrams is that, well, just looking at a few of them suggests maybe there's a smarter way to calculate this. So most of these diagrams, or many of the diagrams at order g to the fourth, just look like diagrams at order g squared stitched together. So if we were going to explicitly calculate some of these diagrams, it probably wouldn't be very hard to calculate this diagram if we knew the result of that one. We just paste together multiple copies. So these are really the new and interesting diagrams that show up at this order. And in a sense, these ones are uninteresting because they're just copies of lower order diagrams put together. And that observation suggests that perhaps there is a simpler way or a better way to organize perturbation theory. So instead of grouping the diagrams together by their order in perturbation theory, what we can do is we can organize the diagrams together by how many places we can cut them so they fall in half. So particularly the key property that distinguishes these diagrams, which are uninteresting diagrams at g to the fourth, from these diagrams, which are the interesting ones at g to the fourth, is the fact that I can cut this diagram, or this diagram, or this diagram, or this diagram here, and it falls into two separate diagrams. For these diagrams, there's no single line that I can cut that will make this diagram into two, make it disconnected. So if I cut any one of these lines on this diagram, it remains connected. So we can organize our perturbation theory in a different way. We can organize it instead of by order in G, we can order it by how many places there are in the diagram so that we can cut it. So any diagram, there'll be some integer number of lines that we can cut that will make the diagram disconnected. And we'll call the pieces of the diagram that remain connected if we cut any one line 1 pi. So this means 1 pi means one particle irreducible. And it means that that part of the diagram remains connected if any one line is cut. And so on these diagrams, this part of the diagram is 1 pi, this part is 1 pi, this part is 1 pi here. And so on. So this is just a statement that there could be there's some number of 1 pi parts in any diagram that contributes to the momentum space propagator. And we can compute this momentum space propagator perturbatively as long as we can compute the sum of all the 1 pi diagrams. So let's suppose we can do that sum. And let's say the sum of all the 1 pi diagrams is minus I times sigma of k squared. And sigma here is sometimes called the self-energy. Okay. So suppose we can compute the self-energy. We probably can't do it exactly, but we could do it at some order in perturbation theory. Then let's try to compute G2 of k. So G2 of k, our first diagram just gives us I over k squared minus m squared plus I epsilon. Okay, so remember, we're just taking the Fourier transform of the position space Feynman rules. So we're including the external propagators because we're not amputating anything. We're not using the LSE formula. So the momentum here is k. And we include the propagator for the external legs. Our second diagram contains two propagators and one copy of the self-energy. And so on. If we go to the next order, we get one more propagator, one more self-energy. And what we're left with is just a geometric series. And the i's and minus i's cancel, get just the self-energy. The n. And we can sum this geometric series. And this is, if we write out the product, can get a simpler form. So we get G2k is I k squared minus m squared minus sigma of k squared plus I epsilon. And so this is a result valid to all orders in perturbation theory. We basically resummed our perturbation theory. And so we unlike our previous result, the Chalian-Lemon result, here we were explicitly drawing Feynman diagrams doing perturbation theory. And so this diagram is the Fourier transform of the Feynman propagator, which involves the mass that shows up in Lagrangian, the mass m squared on the top board. This is involves m squared, but the mass that shows up in the Lagrangian, or sometimes called the bare mass. So here we have two expressions, one valid to all orders in perturbation theory. The other one is exact. And they should agree. So they should agree. And making them agree will give us additional renormalization conditions that we can use to fix some of the coefficients in our Lagrangian. And so let's determine what those conditions are. Okay. So if we compare our two results, we notice that the Chalian-Lemon result tells us that our propagator should have a pole at k squared equals m squared. So if we want m squared equal m physical squared, so this is the whatever shows in Lagrangian equal to the physical mass squared, then we should have that the self-energy evaluated at m squared should be 0. This as a pole at k squared equals m squared plus sigma. So sigma sorry, sigma depends on k squared, but if this is 0 at k squared equals m squared, then there's a pole at k squared equals m squared. So this condition tells us that the location of the pole is correct. And we also want the residue to be correct as well. So over here, the residue is just I. So the residue over here should just be I. And well, the residue will be correct as long as the derivative of the self-energy at evaluated at m squared is 0. Okay. So these are two additional conditions we can impose to determine what our counterterms should be. So we can think about this one as being specifying the physical theory. So it's telling us what the the mass is, and this one is a condition on the normalization of our states. So we can trace this one back to our choice that k phi omega is e to the ikx, and this is specifying the physical theory.
Is that by dk squared? Is that prime?
Yes, it's the derivative with respect to k squared. And so at leading order, we could use these two conditions to fix z phi and zm. So z phi and zm in our perturbative calculation will enter in this diagram. So this diagram at leading order just will be a g squared diagram, and this diagram will be proportional to z phi and zm. So if we demand, these are the two leading contributions to the self-energy, and so we can use those to fix z phi and zm at leading order. If we go to higher order, all our conditions will mix. We'll need to solve them all simultaneously, or the lower order results will feed in. Okay. So far we have 3 conditions on 4 parameters of our theory. 2 of them we can trace back directly to our assumptions in the LSE formula. We assumed that omega phi omega was 0, k phi omega is e to the ikx. That gave us, we had a tadpole condition, this condition on the residue, and we also have this more physical condition on the location of the pole in the propagator. So we need one more condition, and it should involve the coupling. So we have yet to, at leading order, we have none of our conditions tell us anything about ZG. So far, 3 conditions. So 1 tadpole and 2 propagator. And these don't fix ZG at leading order. So we need one more. And our last condition, there's some freedom here. We just basically need to define what we mean by the coupling strength. So and we should do that physically. So we want to match our theory. Well, we don't have to, but for clean interpretation, we would want to impose some physical conditions. So if we wanted to have a direct mapping between what showed up in the Lagrangian and our physical theory, we could impose some condition on a cross-section. Perhaps we could define our coupling strength by being related to the cross-section in for some particular choice of incoming and outgoing momentum. That's one way we could do it. That would turn out to be very difficult in practice. So we could impose a condition on the matrix element or something, some irreducible. It turns out the easiest way to do it will be to directly impose some condition on the irreducible diagrams. And that's a rather long story, which I won't have time to tell you all about in the last few minutes, but it's something we'll explore in great detail in QFD2. The key point is we need one more condition, and we'll overdetermine it if we say that, say, phi to phi scattering scattering is related to the cross-section, related to the coupling in some particular way for all momenta. So the strongest condition we can impose is we can define the coupling at some particular reference scale. So like we did here. So here, the most we could say about this is we could demand that the self-energy at some particular value of the momentum was 0. If we tried to say this for all k, we'd just be completely over-determining our system and everything would fall apart. So the best we can do is impose a condition at some reference momentum, which is going to imply that the effective coupling strength runs or varies with momentum or energy. So this is the idea of the renormalization group, and we'll discuss that in lots of detail in QFD2. There's lots to say about that, which I fortunately can't do in the last few minutes, but that's what we would do. We'd need to impose one additional condition, and in a sense, this is the most interesting of them, of the conditions we need to.
So we impose these conditions in each order in the perturbation theory. So how do we know that there are not going to be important contributions in each order?
Well, so it depends on the value of our coupling. So if our coupling is small enough, then we'd expect, and we'll find in most reasonable cases, that the contributions from higher order will be smaller than the contributions at lower order. That's what you'd expect if your perturbation series is good. But, well, as I briefly mentioned, but also spoke, it's more about in the Math for QFD course. The perturbation techniques we've derived here are give us asymptotic series. So, well, we might expect, even when perturbation theory is good, we'll expect that the contributions will get smaller as we go to higher order, at least for low orders. Eventually, everything's going to blow up. We're, in general, missing non-perturbative contributions here, which are important in a number of contexts. That's something we'll come back to in great detail in QFT3. But the expectation that perturbation theory works is borne out in most reasonable cases. And in fact, I think QFTs give you some of the best examples of where perturbation theory works in physics and really all of any theory of nature we have. Perturbative calculations in QED can be done to 5th or 6th order and to 10 or 11 decimal places. So really spectacular accuracy. But sometimes we'll be interested in strong coupling, in which case all these techniques break down. There are other techniques that sometimes work that we may come back to in later courses. Other questions? Okay, so just about the end. Just like to very briefly summarize what we've done. So my part of the course has essentially been a story of how to calculate observables. So when we started talking about interacting theories, the first thing we talked about was the relationship of the cross-section and decay rate to the matrix elements. Those we can compute using the LSD formula by relating them to time-ordered expectation values in the Heisenberg picture. Going to the interaction picture allows us to compute them by relating them to the Feynman propagator. And so this is the story I hope you keep in mind. And today we've more consistently accounted for this step. So in this step, our derivation of the LSE formula, we made two assumptions. We can consistently impose those in perturbation theory, as we've seen today. And so next week, Gong's going to take over. She's going to tell you a very similar story, but she's going to put her own spin on things when she tells you about particles of spin. So I hope. Thank you.